Section: Introduction. In this section, we discuss the importance of scientific research in the development of artificial general intelligence, AGI, as it has the potential to lead to significant advancements in society. We recognize that AI systems must meet high standards, including the ability to understand various scientific fields, from molecular structures to time series data, and to engage in complex reasoning tasks like hypothesis testing and experimental design. To address these needs, we have developed Intern-S1, an open-source multimodal model designed to tackle complex scientific challenges by processing images, text, and scientific data. Our model has shown superior performance compared to both open-source and closed-source models in scientific tasks involving images and text. We note that while recent models have improved in areas like mathematics and general reasoning, they still face challenges in scientific domains with less available data. We believe it is crucial to explore how we can enhance a model's ability to handle low-resource tasks effectively and at scale. In the pre-training phase, we focus on gathering high-quality data for these valuable scientific areas. We employ two main strategies. First, we use a recall and filtering process to extract relevant data from the web, significantly increasing the quality of our dataset. Second, we utilize a page-level parsing method for PDF documents, which are rich in scientific information, to gather more high-quality data efficiently. After pre-training, we implement reinforcement learning using Intern Bootcamp, a large interactive environment with over 1,000 tasks. We introduce a new algorithm called Mixture of Reward, MORE, to unify feedback from various tasks into a single reward system. This approach allows us to efficiently train the model on both easy and hard-to-verify tasks. By integrating MORE with various reinforcement learning techniques and optimizing our infrastructure, we can train the model effectively with fewer samples, achieving top performance in less time compared to previous efforts. With our diverse data strategies and advanced algorithms, Intern-S1 stands out among current open-source models and competes well with leading closed-source systems. We are excited to share our model weights and tools, aiming to inspire further research in general reasoning and to drive progress in various scientific applications. Section Summary. In this section, we discuss the development of Intern-S1, an open-source multimodal model designed to enhance scientific reasoning and understanding by processing diverse scientific data types. We outline our innovative data curation and reinforcement learning strategies that enable Intern-S1 to achieve state-of-the-art performance in scientific tasks, bridging the gap between open-source and closed-source models while advancing towards artificial general intelligence. Section: Model Architecture. In this section, we describe the architecture of Intern-S1. We utilize the Qwen 3-235B mixture of expert model for our large language model, LLM, and the Qwen 3-8B for Intern-S1 Mini. We categorize scientific data into three types based on their representations and use different methods to project them into the LLM's representation space. For visual data, we use a vision transformer to encode images, a dynamic tokenizer for discrete representations like molecular structures, and a specialized encoder for domain-specific data such as time series signals. For our vision encoder, we choose the Intern-VIT series. Intern-S1 employs the larger Intern-VIT6B, which has been refined through contrastive pre-training and next token prediction, resulting in high-quality visual representations. In contrast, Intern-S1 Mini uses the smaller Intern-VIT300M, which retains much of the larger model's capabilities while being more efficient. These encoders allow us to balance computational power and accuracy, with Intern-VIT6B providing maximum representational strength and Intern-VIT300M offering a good efficiency performance ratio. They can handle fixed input sizes of 448 by 448 pixels or adjust dynamically for high-resolution content. We also use a pixel unshuffle technique to reduce the number of visual tokens, so a 448 by 448 image is represented by 256 visual tokens. These tokens are then aligned with the language model's embedding space through an MLP projector, and the parameters of the vision transformer are jointly trained during the image-text training phases to enhance understanding of visual and scientific data. Next, we introduce our dynamic tokenizer, which formalizes scientific data structures like molecular formulas and protein sequences as tagged sequences. For example, the tagged sequence less than smiles greater than C1CCCCC1 less than smiles greater than represents a molecule. Previous research has shown that these tagged sequences help language models differentiate between various data structures. However, we identified two main issues. The tokenizer uses a uniform splitting strategy for all sequences, and the same token across different modalities shares the same embedding. The first issue limits the model's ability to compress scientific data effectively. For instance, the SMILES format is common in chemistry but not in general text, making it hard for general-purpose LLMs to encode it efficiently. The static tokenizer's one-size-fits-all approach can reduce compression ratios for natural language when favoring scientific modalities. The second issue involves shared embeddings, which can bias representations and hinder performance in scientific contexts. While previous studies have pointed out the drawbacks of static tokenizers and suggested dynamic alternatives, these solutions often face robustness challenges, such as sensitivity to minor contextual changes. We found that these limitations can be significantly reduced when processing scientific modalities, as scientific strings can be easily identified, avoiding contextual sensitivity issues. Our dynamic tokenizer first identifies the input string's modalities and applies tailored splitting strategies for each, concatenating the results into a single input sequence compatible with modern LLM architectures. Currently, Intern-S1 supports 4 modalities, with plans for future expansion. Each modality can be clearly marked with special tags in user input, such as less than FASTA greater than or less than SMILES greater than. We also use heuristic rules and domain-specific tools like RDKit to automatically detect molecular and protein strings. Our experiments show that the dynamic tokenizer is effective, achieving a compression ratio that improves by up to 70% compared to models like OpenAI's GPT-OSS120B, DeepSeek R1, and the Qwen 3 series. We measure tokenization efficiency using the characters per token metric, which quantifies the compression ratio based on the length of the original and tokenized strings. Section Summary. In this section, we describe the architecture of Intern-S1, which utilizes the Qwen 3 to 235B mixture of expert model and incorporates various encoders for different scientific modalities, including a vision transformer for visual data and a dynamic tokenizer for structured scientific data. Our dynamic tokenizer improves efficiency by applying tailored splitting strategies for each modality, achieving up to a 70% higher compression ratio compared to existing models. Section: Time Series Encoder. In this section, we integrate a time series encoder into Intern-S1 to effectively manage sequential numerical data, which often includes measurements taken over time, like seismic waves and EEG recordings. This type of data is usually lengthy, continuous, and lacks clear structure, making it challenging for large language models to process. Our time series encoder captures the relationships over time and compresses the input into forms that are easier for these models to understand. It processes raw signals as continuous numerical values, which can differ significantly in sampling rates, durations, and physical meanings. We include an adaptive downsampling module and transformer-based blocks to create a unified representation of scientific time series signals, enhancing our model's ability to interpret various scientific data alongside image data. For our training infrastructure, we will release it in XTuner, a flexible toolkit for pre-training and post-training of large language models. We organize this infrastructure into 2 main parts: training using next token prediction, which includes pre-training and supervised fine-tuning, and reinforcement learning. In our pre-training and supervised fine-tuning setup, we use fully sharded data parallelism, FSDP, to distribute model parameters across GPUs. We adopt FP8 precision for matrix multiplications, applying dynamic scaling during computations. In the forward pass, we scale inputs tile-wise and weights block-wise, while in the backward pass, we compute gradients using two types of matrix multiplications. We maintain the vision tower in BF16 precision for stability. We also implement several kernel optimizations. 1. A grouped GEM kernel to manage dynamic group sizes in mixture of experts, MO, computations. 2. The Liger kernel, which combines linear and cross-entropy layers for efficiency. 3. Flash Attention 3, which supports variable length inputs to enhance attention computation. To tackle workload imbalances in FSDP during variable length training, we propose a variable length balanced strategy. This involves packing documents into buckets, applying a sliding window to group them, and sorting by maximum length, ensuring balanced computational loads and achieving an average twofold speedup in our training framework. For reinforcement learning, we again use FSDP with one-way expert parallelism to avoid inter-expert communication and manage memory growth. We maintain FP8 precision for both training and inference to enhance throughput. Our architecture collocates training and inference on the same devices, allowing for efficient redistribution of the model during RL steps while keeping optimizer states intact. During inference, we utilize 8-way expert parallelism and implement our serving backend in PyTorch, storing weights in FP8 to minimize memory usage. We enable CPU offloading and continuous batching to maximize throughput, and we dynamically rebalance workloads to prevent delays during decoding. The entire training process for Intern-S1 consists of 4 distinct stages, each with specific data preparation and training strategies. We will detail these stages further. In our text and image text continued pre-training, we sample from a data pool rich in scientific data, as shown in our statistics. We emphasize 3 key components of our pre-training data pipeline, which have been well documented in other technical reports. Section Summary. In this section, we describe the integration of a time series encoder in Intern-S1, which effectively processes sequential numerical data like seismic and EEG recordings by capturing temporal dependencies and compressing inputs for better compatibility with large language models. We also outline our training infrastructure, which employs advanced techniques such as fully sharded data parallelism and FP8 precision to enhance efficiency and performance during both pre-training and reinforcement learning phases. Section: Page-level PDF documents parsing. In this section, we discuss our approach to parsing PDF documents at the page level. We gather PDF files from the Internet and archived libraries, using a combination of optical character recognition, OCR, and vision language models, VLMs, to convert these documents into either image text or pure text formats. We have learned that the quality of parsing is vital for PDF documents, as it significantly affects model performance, particularly in scientific fields where valuable knowledge is often not found in web data. We noticed that parsing issues are more common in documents with numerous equations and symbols. Through our evaluations, we found that no existing parsing tools, whether proprietary or open source, can perfectly handle all PDF types, and their costs vary widely. To achieve a balance between quality and cost, we created a page-level parsing pipeline. Each page of a PDF is first processed by a low-cost parser called minor-u. We then identify pages with many equations and symbols that the low-cost parser struggles with. These questionable pages are sent to a more expensive parser, which includes VLMs like Intern-VL and Quen-VL. We also clean the parsing results using rules or a small language model and combine them with other parsed pages. We implement a global deduplication process to eliminate common pages, such as copyright notices. Despite PDFs being cleaner than web data, we still find that quality control is crucial. Even with powerful VLMs, we detect and remove about 20% of tokens from archived libraries due to garbled text. For web-crawled PDFs, we use an educational scoring system, leading to a 50% preservation rate. Since the high-cost VLMs are significantly slower than the low-cost parser, we only send pages with equations and symbols to them. For archived libraries, 5% of pages are processed by the high-cost parser, while for web-crawled PDFs, this is 3%. Next, we address domain-centric web data parsing. Web-crawled data has been widely used for pre-training, but different URL domains have unique characteristics, making it hard to create a one-size-fits-all parsing solution. Previous studies have classified web pages by topic and format, and we introduce a more detailed approach with our domain-centric parsing pipeline. This pipeline treats web pages from the same URL domain as a cohesive unit and applies tailored strategies using a language model-based agent. We sample hundreds of pages from a domain and use the agent to annotate them. Based on these annotations, we decide whether to discard, rewrite, or keep pages from that domain. We also use common rule-based filtering, deduplication, and quality classifiers at the page level. Our motivation for this approach is that pages from the same domain often share similar parsing challenges, such as issues with code snippets or unique navigation bars that standard filters may miss. Since the LLM-based agent is costly, domain-level parsing helps us identify structural patterns that simpler classifiers cannot, while keeping costs manageable. For scientific data recall and filtering, we aim to improve our model's performance in scientific areas by retrieving and filtering relevant data from open-source pre-training corpora and web-crawled data. We create a 3-level taxonomy tree of data domains and select 6 scientific fields: mathematics, physics, chemistry, life science, earth science, and material science, for detailed processing. We use a strong language model to annotate a subset of data for training lightweight classifiers. We also create in-domain and out-of-domain validation sets for each target domain. The in-domain set comes from the same source, while the out-of-domain set is sourced differently, such as using a PDF for web data validation. These validation sets help refine our data annotation prompts. Our manual evaluations show that the proportion of relevant data in the target domains increased from 2% to 50%, highlighting the success of our recall and filtering methods. Finally, in the image-text captain stage, we compile 2 types of datasets: an interleaved image-text dataset and a purely textual dataset. To ensure high quality, domain diversity, and comprehensive coverage, we source our data from 3 main areas. 1. A multimodal pre-training corpus from Intern-S1, covering various domains like image captioning and document understanding. 2. A textual corpus aimed at maintaining the model's text comprehension and reasoning abilities. And 3. Multimodal scientific data to boost performance in specialized tasks. Overall, we have around 250 billion training tokens, with 70 billion from language data and 180 billion from interleaved image-text data, including 30 billion tokens specifically for scientific data. Section Summary. In this section, we describe our approach to parsing PDF documents and web-crawled data, emphasizing the importance of parsing quality for scientific content and the development of a hybrid pipeline that balances cost and accuracy. We also introduce a domain-centric parsing strategy that customizes processing based on URL characteristics, and we enhance our model's performance in scientific domains through targeted data recall and filtering, resulting in a significant increase in relevant data. Section: Multimodal Scientific Data Pipeline. In this section, we describe our multimodal scientific data pipeline, which builds on a previous text-only pipeline. Our goal is to create a system that 1. Maintains detailed scientific structures like figures, equations, symbols, tables, and charts. 2. Aligns visual elements with the surrounding text at a granular level. And 3. Generates supervision formats suitable for scientific reasoning, such as instruction and exam styles. For exam-style questions across 6 scientific fields, we implement a filter to ensure structural integrity, requiring each sample to include the question stem, options, if any, answers, and explanations. We discard any incomplete instances. We also use rule-based filters to eliminate unclear questions, incomplete options, or answers that do not match the questions. For fill-in-the-blank questions with multiple parts, we utilize large language models like Qwen 2.5 to evaluate the completeness of answers. When processing PDF documents and other data with equations, we check the rendering of symbolic markers to avoid errors. For general image-text pairs, we apply basic filters to catch issues like blank images, blurred figures, or broken links between questions and visuals. Next, we outline our training stages. We adopt a multi-stage training approach to enhance both effectiveness and efficiency. Initially, we focus on text-only training through text continuation pre-training, while subsequent stages involve multimodal joint training, highlighting our commitment to integrating different modalities. To improve training efficiency, we use a batch size warm-up strategy, which helps maintain a good training loss while optimizing for larger batch sizes. Batch size is a key hyperparameter that affects both optimization and efficiency. We face a challenge at the start of training, as smaller batch sizes yield better performance early on, while larger sizes enhance efficiency. Our analysis suggests that the best approach is to start with a small batch size and then switch to a larger one for improved efficiency. Regarding our choice of starting point, we build on existing open-source models like Qwen 3 and Intern-S1. These models come in base and instruction versions, and our findings indicate that instruction models perform slightly better. We explore whether better initial performance leads to higher final performance and if initial output diversity impacts the reinforcement learning (RL) process. We conduct experiments with a small model under 4 scenarios, including fine-tuning and continuing pre-training for both model types. Our results show that the instruction model excels in coding benchmarks. We identify 2 scenarios, one where post-training activates existing capabilities in the base model, leading to similar outcomes regardless of the starting point, and another where it enhances capabilities, favoring the instruction model. We also consider output diversity, noting that initial entropy is vital for the RL process, affecting hyperparameter choices and performance limits. We compare fine-tuning a base model directly with continuing pre-training and then fine-tuning an instruction model. Our findings indicate that the base model has slightly higher initial entropy, but this difference can often be adjusted through tuning and is unlikely to lead to significant performance differences. In summary, we conclude that using the instruction model as the starting point is acceptable for final performance after supervised fine-tuning and RL, and it is preferable when post-training significantly enhances model capabilities, although this effect is domain-specific. Section Summary. In this section, we describe our development of a multimodal scientific data pipeline that integrates image and text to maintain scientific structure and enhance reasoning through structured supervision. We also outline our training strategy, emphasizing the use of instruction models for better performance, while addressing the balance between batch size and training efficiency, and the impact of initial model choice on final outcomes. Section: Hyperparameters. In this section, we explore the hyperparameters within our XTuner training framework, focusing on the batch scheduler and learning rate settings. We found that the warm-up stable decay (WSD) approach for the learning rate scheduler is popular because it separates the schedule from the total training data. Our research shows that when using a gradient-based optimizer with a WSD scheduler, the gradient noise and batch size must meet a specific relationship for the model to reach a desired training quality, meaning the loss converges to a certain value. We identified that there is a power law relationship between the gradient noise and loss, indicating that the batch size should gradually increase throughout pre-training. After evaluating training efficiency, we adjusted the batch size from 66 million to 132 million tokens. We determined the optimal time to make this change was after processing 400 billion tokens, ensuring we maintained computational efficiency. Next, we focused on setting the learning rate under the WSD scheduler. Typically, we find an optimal learning rate using smaller resources before applying it to larger models. However, this can be sensitive to various training conditions. To address this, we developed a method for setting the learning rate based on scaling laws, establishing a relationship between training loss and learning rate at each step. We formalized this as an optimization problem, leading us to determine the learning rate for the entire pre-training process. During the entire text captain process, we maintained strict control over training data quality and hyperparameter settings, resulting in well-managed pre-training for Intern-S1 without any loss spikes. We predicted the final training loss to be around 1.16, and it actually fell between 1.17 and 1.18, showing our precision in controlling pre-training quality. After the text captain stage, we optimized the integration of multimodal data, such as image text and video text pairs, alongside large-scale text corpora. Unlike traditional methods that freeze certain model layers, we updated all parameters during the multimodal captain process. We used a transformer-based model that processes text, images, and videos together, employing a left-to-right autoregressive objective for training. Visual tokens served only as context for text prediction, encouraging the model to effectively combine multimodal information for language generation tasks. Following the multimodal CPT, Intern-S1 underwent a two-stage post-training process, mixing text and multimodal data to enhance performance across benchmarks. In the post-training phase, we first applied offline reinforcement learning on carefully selected instruction data, using best-of-N sampling to ensure high-quality responses based on criteria like accuracy and fluency. We also experimented with different data mixtures to optimize performance, treating this stage as offline RL to emphasize the rewarding nature of our sampling approach. Section Summary. In this section, we detail our investigation into hyperparameters within the XTuner training framework, focusing on the warm-up stable decay learning rate scheduler and its relationship with batch size and gradient noise to optimize training efficiency. We also describe our approach to multimodal training, where we jointly update all model parameters and outline our post-training process, which includes offline reinforcement learning to enhance performance across text and multimodal benchmarks. Section: Text-only data. In this section, we emphasize the significance of high-quality and diverse instruction tuning data. We recognize that even a few low-quality or harmful samples can negatively impact model performance, while a more varied and balanced dataset tends to produce better results. To address this, we have developed a data pipeline focused on ensuring both diversity and quality in our instruction data. For our Intern-S1 model, we carefully design the instruction distribution and conduct extensive experiments to identify the best training dataset. Our data pipeline consists of three main components: filtering, labeling, and enhancement. In the filtering stage, we use both rule-based and model-based methods to remove data that could disrupt training, such as repetitive phrases or incorrect information. Next, we implement a labeling strategy to aid in data selection, categorizing data by type and difficulty. We create a hierarchical labeling system with at least 3 levels, such as mathematics, advanced mathematics, and linear algebra. A labeling model classifies the data into these categories and extracts contextual information for scenario labels, like linear algebra proof exercise. For data with known answers, we assess difficulty based on pass rates from a small model. For data without known answers, we establish specific criteria to assign difficulty levels. We then use stratified sampling to ensure a balanced distribution of categories and difficulty levels. If certain areas lack sufficient data or have too many low-quality samples, we either reconstruct responses or generate synthetic data to fill the gaps. This process results in a candidate dataset that includes various categories such as agent, code, general dialogue, and more. We conduct thorough experiments with this dataset to find the best combinations. For our multimodal data, we utilize the same vision language instruction data as Intern-VL3, which includes specialized data for tasks like 3D scene understanding and scientific reasoning. We enhance this data with stricter quality controls to improve the long-thinking capabilities of Intern-S1. Next, we explore the optimal mixture of our curated text and multimodal instruction data to achieve balanced performance across different benchmarks. We validate the effectiveness of each dataset incrementally, starting with a core dataset from Intern-S1 and adding domain-specific subsets while monitoring performance improvements. After confirming the effectiveness of individual datasets, we merge them and fine-tune hyperparameters to resolve any conflicts and optimize training configurations. We begin with initial ratios and adjust them based on performance, using techniques like style alignment and curriculum learning. During training, we apply random JPEG compression augmentation and set a maximum context length to enhance the model's ability to handle long-range dependencies. In the second stage of our post-training process, we implement online reinforcement learning using a mixture of rewards framework. This approach allows us to integrate various reward signals from multiple tasks, helping the model develop both specialized and general capabilities. We address challenges like differing task difficulties by using a hybrid offline-online data filtering strategy. We assess each task's difficulty and convergence speed, determine the final data mixing ratio, and ensure that our training process remains efficient and balanced across all tasks. Section Summary. In this section, we outline our comprehensive data pipeline for instruction tuning, emphasizing the importance of high-quality and diverse data to enhance model performance. We detail our processes for filtering, labeling, and enhancing both text-only and multimodal data, as well as our strategies for validating and optimizing data mixtures and training configurations to ensure robust performance across various tasks. Section: Large-Scale Sandboxes. In this section, we describe our approach to large-scale sandboxes in Intern-S1, where we use Intern Bootcamp to create a variety of synthetic reasoning tasks. These tasks cover areas like algorithms, character reasoning, cryptography, graphical puzzles, board games, logical reasoning, and scientific scenarios, including physics, chemistry, and medical reasoning. We have developed over 1,000 tasks with unlimited training data generated by our Bootcamp case generator. Each task is supported by more than 100,000 training samples, which we refine using heuristic rules, resulting in over 20,000 samples for our mixed reinforcement learning training. For instruction following, which is crucial for model generalization, we rely on verifiable reward signals. We utilize a dataset that provides instruction data with a balanced difficulty level. To filter out easy and overly challenging cases, we calculate pass rates using the SFT model and select prompts with scores between 0.2 and 0.8. This data reward mechanism helps improve our model's instruction following performance. To boost reasoning capabilities, we create a high-quality multitask, multimodal dataset for reinforcement learning with verifiable rewards. For text data, we enhance mathematical reasoning by using questions from various open-source datasets and our internal university-level data. For multimodal data, we gather samples from different areas, including visual question answering, science reasoning, and document understanding. We also convert some text questions into images for training and change multiple-choice questions into fill-in-the-blank formats to reduce guessing noise. All questions in these tasks have verifiable correct answers, and we use the Compass verifier for evaluation and reward assessment, combining it with a rule-based verifier to ensure accuracy. In terms of policy optimization, we note that recent advancements in long chain of thought reinforcement learning have shown improvements in reasoning tasks, particularly with GRPO and its variants. However, these studies mainly focus on dense models, leaving the challenges of applying reinforcement learning to mixture of experts, models less explored. We find that directly applying GRPO-style algorithms to large-scale models can lead to significant training instability due to differences in the computational processes of inference and training engines. This discrepancy is amplified by dynamic expert routing and quantization methods, causing a mismatch between the experts used during inference and training. To address these challenges, we adopt our Oriel algorithm, which uses supervised fine-tuning for positive samples and policy gradients for negative samples without relying on token-level clipping. However, applying Oriel to large-scale models introduces new difficulties, particularly the need for an online token-level reward model, which increases computational demands. To speed up training, we eliminate this model, but this leads to a rapid decrease in entropy, causing the policy model to lose its exploratory ability and settle on suboptimal solutions. To counteract this, we incorporate strategies from recent research on policy drift and entropy mechanisms. We enhance our reinforcement learning loss function with a KL divergence constraint, applied selectively to tokens within a specific covariance range. This approach helps maintain exploration capabilities while preventing entropy collapse during training. Our overall objective includes a supervised fine-tuning loss for positive samples, a policy gradient loss for negative samples with an advantage estimate, and an entropy control term. We also use weighting coefficients to balance the contributions of the supervised fine-tuning and policy losses. Section Summary. In this section, we describe our use of Intern Bootcamp to create over 1,000 large-scale synthetic reasoning tasks across various domains, enhancing instruction following capabilities through a balanced dataset and verifiable rewards. We also address the challenges of applying reinforcement learning to large-scale mixture of experts, models, proposing a modified Oriel algorithm that incorporates KL divergence constraints to maintain exploration and prevent policy collapse during training. Section: Hybrid Data Filtering Strategy. In this section, we discuss our hybrid data filtering strategy. Recent studies have looked into different online and offline methods for filtering reasoning data. We combine these methods to enhance our training data. For the offline filtering phase, we start by running rollouts on our raw dataset using both a smaller dense model and a larger mixture of experts model. Each question is generated 8 times, and we compare the answers to reference solutions to calculate pass rates. We discard questions that are too easy, indicated by a pass rate of 1, and also remove those with low pass rates, as they often contain unclear questions or incorrect answers. In the online filtering phase, we process questions in groups of 8 rollouts. We eliminate groups where all responses are either completely correct or completely incorrect. We also remove samples with unclear text or repeated phrases, as training on such data can lead to issues. To test our filtering strategy, we conducted experiments on the Quen 2.5 model with mathematical data and compared it to DAPO. Our strategy showed a much faster improvement on the evaluation set than DAPO's method, so we applied it to all our training data. Next, we address entropy control, which is vital for model exploration during reinforcement learning training. While DAPO uses a clipping mechanism to manage entropy, it doesn't work well with our model due to inconsistencies. We use a KLCOV entropy control strategy to maintain exploration. Since the original parameters were for a model with high initial entropy, we adjusted them for our Intern-S1 model, which had lower initial entropy. We increased the entropy control coefficient and set specific values for the effect token ratio and KL coefficient. This adjustment kept the model's entropy around 0.2 while improving correctness across evaluations. For the training details of the Intern-S1 model, we used the data mentioned earlier. In open-ended dialogues, we applied a chain-of-thought approach, scoring only the content after the think segment. We treated samples with positive scores as positives and the rest as negatives. We used FP8 quantization for efficiency and generated 8 responses per prompt, with a training batch size of 4096 divided into mini batches. We employed the ADAM-W optimizer with specific learning rates and weight decay, freezing certain model parameters during training. We trained for 600 steps and applied a gradient norm filter to exclude noisy samples, dropping about 3% of the training data. Finally, we selected the best performing checkpoints and averaged their weights for improved performance. In our evaluation, we conducted extensive tests across various benchmarks, focusing on both general and scientific reasoning tasks. We will outline our evaluation setup, describe the benchmarks, and compare the performance of Intern-S1 with other leading models. Section Summary. In this section, we describe our hybrid data filtering strategy that combines offline and online methods to refine training data, discarding overly simple or noisy questions and ensuring the quality of samples used for model training. We also detail our entropy control mechanism to maintain exploration during reinforcement learning, alongside the training specifics and evaluation benchmarks used to compare our model's performance against state-of-the-art approaches. Section: Evaluation Configuration. In this section, we evaluate our models using VLM EvalKit and OpenCompass. Unless stated otherwise, we activate the thinking mode. To reduce repetition from greedy decoding, we use a sampling decoding strategy, setting the temperature to 0.7 for Intern-S1 and 0.8 for Intern-S1 Mini. For our benchmarks, we choose a variety of influential benchmarks that cover both general and scientific reasoning. We include recent scientific reasoning benchmarks from key fields such as mathematics, physics, chemistry, life sciences, materials science, and earth science. These benchmarks, which include both text-only and multimodal formats, allow us to compare professional reasoning across leading models. Below, we briefly introduce each benchmark. MMLU Pro enhances the original MMLU by focusing on reasoning rather than just recall. It increases answer choices to 10, removes irrelevant items, and includes over 12,000 questions across 14 domains, making it a tougher and more reliable benchmark for model comparison. GPQA consists of 448 expert-written, graduate-level multiple-choice questions in biology, physics, and chemistry. It is designed to be challenging even for non-experts with internet access, making it suitable for assessing deep knowledge and reasoning. We evaluate using the Diamond subset. AIME 2025 includes 30 short answer problems from the American Invitational Mathematics Examination, where each answer is an integer between 000 and 999. This benchmark is commonly used to assess mathematical reasoning on small, difficult test sets, and we utilize the version collected from OpenCompass. IF-Eval assesses instruction following through verifiable constraints, cataloging 25 types of instructions across about 500 prompts for objective and reproducible automatic scoring. MathVista focuses on mathematical reasoning in visual contexts, combining 6,141 examples from 28 existing datasets and 3 new ones, requiring detailed visual understanding and compositional reasoning. MMMU is a multimodal benchmark with 11,500 college-level questions across 6 core disciplines, 30 subjects, 183 subfields, and 30 types of images, aimed at testing advanced perception and domain-specific reasoning. MathVision compiles 3,040 competition-style math problems with visual contexts across 16 disciplines and 5 difficulty levels, highlighting significant gaps between current language models and human performance in multimodal math reasoning. MMStar is a benchmark of 1,500 human-curated items that require images to solve, balanced across 6 core capabilities and 18 axes, and it includes metrics to measure true multimodal improvements. SMOL Instruct is a large-scale instruction tuning dataset for chemistry focused on small molecules, covering 14 carefully chosen tasks and approximately 3.3 million query response pairs, using both SMILES and selfies formats. We evaluate using the official test split. ChemBench is an automated evaluation framework with 2,788 curated question-answer pairs in undergraduate and graduate chemistry, designed to assess the knowledge and reasoning of language models against expert chemists. MatBench is a standardized test suite with 13 supervised tasks for predicting materials properties, drawn from 10 open datasets, featuring fixed splits and a reference baseline for fair benchmarking. Protein LM Bench includes 944 manually verified multiple-choice questions about protein sequence, structure, and function, providing a focused benchmark for evaluating protein understanding in language models. SFE, or Scientist's First Exam, tests scientific cognition in language models across perception, attribute understanding, and comparative reasoning, consisting of 830 expert-verified visual question-answering items across 66 tasks in 5 disciplines. Physics benchmarks foundational models on 1,297 PhD qualifying exam physics problems, including 298 multimodal items, with automated checks for symbolic equivalence to verify answers. Micro-VQA is a multimodal benchmark centered on microscopy, featuring 1,042 multiple-choice questions across various imaging modalities and biological topics, aimed at scientific analysis and reasoning. Finally, MS Earth MCQ is the multiple-choice subset of the MS Earth Science benchmark, offering approximately 2,780 expert-derived questions related to the atmosphere, cryosphere, hydrosphere, lithosphere, and biosphere. XLRS Bench evaluates language models on ultra-high-resolution remote sensing images, with an average size of about 8,500 by 8,500 pixels, featuring human-verified annotations across diverse tasks that reflect real-world remote sensing scenarios. Section Summary. In this section, we evaluate our models using VLM EvalKit and OpenCompass, employing a sampling decoding strategy to reduce repetition and selecting a diverse set of benchmarks that cover various scientific disciplines to ensure a comprehensive assessment of reasoning capabilities across top-tier models. Each benchmark, such as MMLU Pro and GPQA, is designed to rigorously test different aspects of knowledge and reasoning, providing a robust framework for comparison. Section: Performance Comparison. In this section, we compare Intern-S1 with recently released large language models, LLMs, and vision language models, VLMs, including both proprietary and open-source options. Intern-S1 demonstrates top-tier open-source performance and competes well with proprietary APIs, particularly in scientific reasoning. On general reasoning benchmarks, Intern-S1 stands out as the leading open-source multimodal model across all 8 tasks, achieving the highest score on MathVista with 81.5. It significantly surpasses previous open-source models, for instance, by 2.5 and 6.7 points on MathVista compared to Intern VL3 to 78B and Quen 2.5-VL72B, and by 19.4 and 24.4 points on MathVision. However, it still falls short of the best API models in text-only GPQA and IF-Eval, while remaining competitive in AMI 2025. For science-focused text-only benchmarks, Intern-S1 excels overall in 3 out of 4 datasets. SMOL Instruct with 51.0, ChemBench with 83.4, and MatBench with 75.0, showing large improvements over previous open-source models, such as a 25.7-point lead on MatBench compared to Intern VL3 to 78B. In science-focused multimodal benchmarks, Intern-S1 achieves the best scores in 4 out of 5 datasets. SFE with 44.3, Micro-VQA with 63.9, MS Earth MCQ with 65.7, and XLRS Bench with 55.0, while ranking second in physics with 44.0, trailing behind the leading model. The improvements over open-source baselines are consistent and significant. Overall, these results suggest that Intern-S1 significantly reduces the gap to closed-source large models in general reasoning and sets a new standard for open-source multimodal scientific reasoning, although there is still room for improvement in instruction following tasks. Next, we compare Intern-S1 Mini with recently released open-source LLMs and VLMs, including Quen 3 to 8B, GLM 4.1 volts thinking, and MIMO VL7 BRL 2508. In general reasoning for text-only tasks, Intern-S1 Mini establishes a new open-source benchmark across several text-only evaluations: 74.8 on MMLU Pro, 65.2 on GPQA, and 80.0 on AMI 2025. These results reflect strong factual reasoning, competitive math skills, and effective instruction following. For general reasoning in multimodal tasks, Intern-S1 Mini achieves the best open-source score on MMMU with 72.3. Its performance on MathVista and MathVision is competitive but falls behind GLM 4.1 volts thinking, and it is 7.7 points behind MIMO VL7 BRL 2508 on MM*, indicating there is still room for improvement in visually intensive math problems. In scientific reasoning for text-only tasks, Intern-S1 Mini shows significant gains on domain-specific benchmarks, scoring 32.2 on SMOL Instruct, 76.5 on ChemBench, 75.0 on MatBench, and 63.1 on Protein-LM Bench, all surpassing the strongest open-source baselines. These consistent margins highlight its strong scientific knowledge and reasoning abilities. In the multimodal scientific suite, Intern-S1 Mini achieves the best scores on 4 out of 5 datasets: Physics with 28.8, Micro VQA with 56.6, MS Earth MCQ with 58.1, and XLRS Bench with 51.6. Overall, across 17 benchmarks, Intern-S1 Mini secures the top open-source score in 11 of them, matching or exceeding the strong text-only LLM Qwen 3-8b and remaining highly competitive with contemporary VLMs. These results indicate that Intern-S1 Mini is not only a strong general-purpose VLM but also an excellent lightweight scientific reasoner, and we anticipate that this powerful multimodal model will support a wide range of science-related tasks.